So this is part 2 to chapter 7, the structure and synthesis of alkenes and elimination. So the first video covered all the way from alkene characteristics, elements of unsaturation, nomenclature of alkenes, easy nomenclature, stability of cycloalkenes, heats of hydrogenation. So all of that is in part 1. Part 2, now we're going to have a focus on the alkene synthesis, on how we even create alkenes. So there are 3 main mechanisms that we are going to focus on. We're going to focus on E1 and E2 reactions, which are elimination reactions. And we're also going to focus on the mechanism for the dehydration of alcohols, in which we'll also create an alkene. There are 2 other methods that are not listed right here in the alkene synthesis overview, which is catalytic cracking and dehydrogenation. And it's because you don't really need to know the mechanism for that. We'll really just cover the main concepts. But jumping into elimination reactions. So elimination reactions is also called dehydrohalogenation. So if we break that word apart, dehydro, the removal of a hydrogen, and halogenation, and the removal of a halogen, is going to form a double bond. So we have E1 and E2, and we're going to pause right here. We're going to rewind to chapter 6, where we talked about SN1 and SN2 reactions. So those were substitutions where we were adding to our structure. But for the most part, if you remember SN1 and SN2 reactions, E1 and E2 kind of are going to have a similar flow to as our SN1s and SN2s. So there's a lot of similarities between these 2 reactions. So E1 is unimolecular, and the reason is because the rate of reaction is just dependent on the concentration of your alkyl halide. Whereas E2 reactions are bimolecular, that's what the 2 stands for, and it's because our rate of reaction is dependent on the concentration of our alkyl halide and our base, which is also going to act as our nucleophile. That is going to be our attacker. So because E2 reactions, the rate of reaction is dependent on the concentration of your base, E2 reactions must have a strong base. It requires a strong base, whereas E1 reactions do not require a strong base. Now looking at the order of reactivity for our alkyl halides. For E1 reactions, tertiary and secondary alkyl halides will be favored. Tertiary will undergo E1 reactions the quickest, whereas secondary alkyl halides will moderately undergo E1 reactions. However, primary alkyl halides cannot undergo an E1 reaction. However, E2 reactions can undergo tertiary, secondary, and your alkyl halide can be tertiary, secondary, and primary, and it can still undergo an E2 reaction. However, this mechanism is concerted, so as our base is abstracting a proton, then we're going to create our double bond, and our leaving group is going to leave. Everything is happening at the same time. And because this is happening at the same time, we cannot undergo any rearrangements. However, E1 reactions, they are multi-step. We're going to generate a carbocation intermediate where we're going to favor the tertiary and the secondary carbocation. And so because we generate a carbocation intermediate, we can undergo rearrangements, which is something that we saw in chapter 6, where we could undergo a hydride or a methyl shift, so that way we could create a more stable carbocation. E1 reactions do require a good ionizing solvent, such as water or an alcohol. So anytime you see an alkyl substrate that's reacting with ethanol or is reacting with water, that should be a huge key indicator that this can be an E1 reaction. However, E2 reactions, because we have a strong base, we're not really focusing on ionizing. We're not really creating a carbocation. Lastly, we're going to talk about two rules that we are going to introduce. This is new. E1 is going to follow Zaitsev's rule. So, because we are creating double bonds, we can have more than one product. And in the event that we have two or more products, Zaitsev's rule states that in an E1 reaction, the more substituted alkene is going to be favored. However, in E2 reactions, they can follow Zaitsev's rule, or Hoffman product. And so Hoffman product also says, in the event that you have two or more final products and you're using a bulky base, the least substituted alkene is favored. So let's go on ahead and jump into the mechanism for E1 reactions. So the first step is our leaving group is going to leave and our carbocation is going to form through ionization. So what if I had tert-butyl chloride and I am going to react it with ethanol. So dissecting my alkyl halide, I see that my chlorine is attached to this carbon, which then in turn is connected to three other carbons. So I have a tertiary alkyl substrate. So we love that. Also, I have ethanol. Ethanol is an alcohol, which is a good ionizing solvent. So this lets me know right here that this is definitely going to be an E1 reaction. So since this is an E1 reaction, we're going to have we're going to generate a carbocation intermediate. So the first step, our leaving group leaves, and that's going to generate our carbocation. And we see that we have generated a tertiary carbocation that's as stable as we can get. So now, once you have generated your most stable carbocation, moving on to our second step, our weak base, which is still a good ionizing solvent, ethanol, but alcohols are kind of weak bases, they're going to depronate. We're going to remove a hydrogen from our intermediate to give an alkene. So I am going to stretch out one of these methyl groups, just so that way we can see where we're pulling from. So, again, we are not attacking any carbons. We are just removing a hydrogen. We are just abstracting. So our oxygen from our alcohol is going to come over here and grab this hydrogen, and the bond between the carbon and hydrogen, the hydrogen we just pulled from, it's now going to fold between our carbon and carbocation, and it's going to form a double bond. So whenever we do that, our final result is going to look something like this. And so we only have one final product because we only created one intermediate, but we can see that this is di-substituted since we have two alkyl groups attached to our double bond after our carbon. So that is an example where we did not undergo any rearrangements because we were already tertiary. But let's go over an example where we should undergo a rearrangement. Oh, I'm just going to make some space right here. All right. So what if we have 2-bromomethylbutane, which you should know how to draw that. Two-bromo-3-methyl, by the way. 2-bromo-3-methylbutane, and it's going to react with water. I've got a secondary alkyl halide, so I know that can undergo an E1 reaction, and water is a good ionizing solvent. So I know that this is going to be an E1 reaction. So the first step is our leaving group is going to leave, and we're going to generate our carbocation intermediate. Now, since our alkyl halide was secondary, whenever our bromine leaves, we're going to generate a secondary carbocation. Now, I'm going to go on ahead and add the hydrogens that are already existing. And we can see that we can undergo a hydride shift to generate a more stable intermediate because we are currently secondary. However, if we undergo a hydride shift, our carbocation has now become tertiary. Now that we have generated our most stable intermediate, we are now ready for our water, for our weak base but good ionizing solvent, to come and abstract our hydrogens. So, looking at my tertiary product, there are two different places where I could abstract my hydrogen. If I look at what's surrounding my carbocation, right here I've got a secondary carbon. Over here I've got a primary carbon, and this is also primary as well. So that is what is all surrounding my carbocation. So there are two different products that I can generate. I could either abstract from my secondary or I could abstract from my primary. And we are going to do both so that way we could see how we can apply Zaitsev's rule. So pulling from my primary carbon first, you're going to abstract the hydrogen, and the bond between the carbon and hydrogen is going to fold down between your carbocation to generate your double bond. So that is going to be product number 1. However, I am going to change my color. If I were to abstract from my secondary carbon, I grab my hydrogen, the bond between the carbon and hydrogen is going to fold down in between my carbon and carbocation, where I've now created a double bond. So, these are my two final products. And if we look at our first structure that we created, we've got only 2 hydrogens over here. So we've got a methyl group right here, and then an ethyl group. So this is disubstituted. And looking at our second structure we created, we've got a hydrogen. We've got 1 methyl group, 2 methyl groups, 3 methyl groups. So this would be trisubstituted. And if it helps you drawing it kind of more like Lewis structure, this is what it would look like. where you can see your two alkyl groups. And then over here, you can see our three methyl groups to see how we are tri-substituted over here. 1, 2, 3. So that is an example of the E1 reaction with without undergoing a rearrangement and also undergoing a rearrangement. So the next mechanism that we're going to move on to is the E2 mechanism. Again, this is a concerted reaction, so all of our bonds are forming and are breaking all at the same time. So it's going to be very, very quick. However, it is important to note, which I did not write down, that E2 reactions have a certain stereochemistry that they should follow, which we call anti-coplanar. I'm going to write this down real quick. Anti-coplanar, anti being 180 degrees, kind of like our Newman projection, and then coplanar meaning they're on the same plane. So this is very important. We want our halide and our hydrogen to be anti-coplanar because whenever we're in the stereochemistry, it allows our pi bond to form whenever our hydrogen and whenever our halide are aligned, since this is all happening all at once. So it helps minimize the steric hindrance between our leaving group and our base, and it also just gives stereo-specific results. So again, just know that E2 mechanisms, you want your halogen and your halide to be anti-coplanar. So I'm going to do an example where I'm going to use the stereochemistry to kind of show you what anti-coplanar looks like. So what if we were to have 3-bromopentane, Geez, I got a heavy hand. So we've got our 3-bromopentane, and it's going to react with sodium ethoxide. And excuse me, this should not be a methyl group. This should just be a hydrogen. So looking at our alkyl halide, it is secondary, and we know that E2 reactions, a secondary alkyl halide can undergo an E2 reaction. But looking at our sodium ethoxide, this can break apart into the sodium ion and the ethoxide, the ethoxy ion. So we've got our oxygen bearing a negative charge. We know that this is a strong base, and so we know for a fact that this is going to be an E2 reaction. So what's going to happen is, again, we're just abstracting. We're focusing on grabbing hydrogens. We're not focusing on attacking our carbons. So our ethoxy ion is going to come and abstract this hydrogen. The bond between our carbon and our hydrogen is going to fold between the two carbons to make a carbon-carbon double bond. And then the carbon and bromine bond is going to leave. Our bromine is going to leave, and we're taking the bond with it. So I'm going to draw the transition state for those that like to see kind of where all of the bonds are forming and breaking. So we're breaking the bond between our carbon and hydrogen, which is going to form between our oxygen and hydrogen, our ethoxy. We're going to form a carbon-carbon double bond, and the bond between our carbon and our bromine is going to break because that's going to leave. And we'll just be left with the rest of our structure. So that is what our transition state looks like. And our final result we'll have our carbon-carbon double bond, our hydrogen and our methyl group, and then on the right side we'll have our ethyl group, and our hydrogen. So now we have created pent-2-ene. I'm going to go over another example where we are kind of focusing on less of the stereochemistry. I just kind of wanted to show you what our anticoplanar, what this looks like, where we could see our hydrogen that we've extracted and our bromine, how they're 180 degrees from each other, and they're coplanar, yet they're still on the same plane. Alrighty, so our next example is we're going to have 2-bromo-2-methylbutane. And it's going to react with tert butoxide. The tert stands for tertiary. So this base is going to be tertiary. And if I were to draw this structure out, we could see that this is a very, very bulky structure. This is what we would call a strong and bulky base. We see it's tertiary. We've got all of this carbon branching right here. This is tertiary. This is bulky. So this should be a few indicators that this is going to be the E2 mechanism. Our alkyl halide is secondary. Secondary alkyl halides can undergo an E2 reaction. Not only do we have a negatively charged base, meaning that this is a strong base, it is also bulky. It's tertiary. So this lets me know that this is E2, and we're going to follow Hoffman's product. I always spell Hoffman wrong. So that's how we could dissect our base and our alkyl halide to let us know what we should be looking out for. So again, this is a concerted reaction, so all of our bonds are forming and breaking at the same time. However, what you want to do is you want to kind of look at what's surrounding your leaving group, right? Our leaving group is attached to this carbon. And to the right of our carbon, we have a primary carbon right here. And then this carbon is tertiary. So these are the two carbons in which we could pull a hydrogen from. So that way we could get our two different products. So if I were to abstract the hydrogen from our tertiary carbon, the bond between our carbon and hydrogen is going to fold between our two carbons to make a double bond. And then at the same time, our leaving group is going to leave. So whenever we do this, I'm left with two methyl groups on the left side of my double bond. And then on the right side of my double bond, I'm left with a hydrogen and a methyl group. So this right here would be a tri-substituted final product. However, if I were to pull from one of my primary carbons, and I'm going to expand that CH3 so that way we can see all of our hydrogens. Again, my tert butoxide, my very bulky base, is going to abstract a primary hydrogen. We're going to make a carbon-carbon double bond, and our leaving group is going to leave. So attached to the right side of our carbon-carbon double bond is going to be two hydrogens. And then on the left side of our carbon-carbon double bond, which is being formed right here, we're going to have one hydrogen and then a CH3 too. So this structure right here is monosubstituted. And since we are following Hofmann's product, because we are using a bulky base, Hofmann's product states that we are going to favor the least substituted product. So our product in purple, which is monosubstituted, is going to be the favored product. So I hope that this is somewhat making sense. And those are the mechanisms for E1 and E2 reactions. So next we're going to talk about the dehydration of alcohols. So dehydration literally means the removal of water. And so for this mechanism, we're going to need a strong acid such as really concentrated sulfuric or phosphoric acid in order to pronate our alcohol, our OH group. Now, the reason is because OH, our alcohol, is a poor leaving group. So whenever we pronate our OH group, it's then going to bear a positive charge. So then it can leave the entire structure. And so we're going to go over, of course, the mechanism, and it's going to follow the E1 mechanism. I'm going to make this a little bit smaller so that way you can see whenever we pronate, sorry. So here we've got our alcohol, and we're going to react it with very concentrated sulfuric acid. So again, we're not attacking anything. The first thing that we need to do is pronate our OH group. We need to pronate our alcohol because it is not strong enough all by itself to leave on its own. It cannot just leave from our substrate like our alkyl halides can. Our halogens are strong enough. They've got all the electrons they need to pull off of our substrate. However, alcohols do not. They are not strong enough to do that. So what we can do is our oxygen can abstract a hydrogen from our sulfuric acid. And whenever we do that, we see that our oxygen is now making 3 bonds. And whenever oxygen has 3 bonds and 1 pair of electrons, or 1 lone pair, it generates a positive charge. Now, we are strong enough to leave. So this is going to go to step 2. Now that our OH is pronated, we're able to pull ourselves, remove ourselves from our substrate, and this is going to ionize and give us a carbocation. And it's also going to leave us with water. We just pulled an H2O off of our substrate. And this is going to be our solvent. So what's going to happen now is our water, our solvent, which is a good ionizing solvent, is going to then abstract a surrounding hydrogen, which is going to create a hydronium ion, we remove our hydrogen. The bond between our carbon and hydrogen is now going to fold between our 2 carbons, giving us a double bond. And that is our final product. So that is an example of dehydration of alcohols. Again, it does follow the E1 mechanism. So in the event that you can do a hydride or a methyl shift to get a more stable intermediate, you would definitely want to do that. And you would want to go with the product that creates that has the more substituted alkene. So lastly, a few other methods that we could use to synthesize alkenes. There's catalytic cracking and the dehydrogenation of alkanes. So catalytic cracking is essentially just cleaving really long chains of alkanes to form a double bond. So if we were to have octane, so what we could do is we could cleave this long chain, and then we would create we would have pentane, and your shorter chain would have propene. Your shorter chain is what gets your double bond. Of course, this does need to be done in the presence of heat and a catalyst. However, catalytic cracking is not really a useful or reliable method that we could use in lab because it just creates a grand mixture of products. So it doesn't really create pure alkenes. It has to be separated, and it just goes through this really long process that's not useful for lab. And kind of the same as dehydrogenation of alkanes. This is just the removal of two hydrogens in the presence of a catalyst and heat to form a double bond. This is an endothermic reaction, but it has a very unfavorable enthalpy, but then it has a favorable entropy, so it's very spontaneous. But you just have to use excessive amount of heat to really push past, to really get past that activation energy. So again, it's not the best method, and it still gives a lot of mixtures. So it's not really favorable. However, the overall mechanism just kind of looks like this. Essentially, here are your two hydrogens. And in the presence of a catalyst, I put platinum, and heat, you'll create an alkene, and you'll have your hydrogen as your side product. That's just an overview. Again, for catalytic cracking and dehydrogenation of alkanes, you don't really need to know the mechanism. Just know the general idea. Know these are other methods that can be used to create alkenes. However, they are not very favored in the lab just because of the big mixture of products. So this is going to conclude Chapter 7, Part 2 of the structure and synthesis of alkenes, where this video focuses on the reaction mechanisms, elimination reactions, the mechanism for the dehydration of alcohols, and then our two other techniques to synthesize alkenes. If you have any questions, please feel free to reach out to me.